Uh, okay. And let me just hide my meeting controls so I don't. Okay. Can you, everyone see my little laser pointer and screen?
Yeah.
Cool.
Okay. It's a great pleasure to have Seth Musser as our speaker today. Seth just finished his PhD from MIT this summer, and now he started as a postdoc at University of Maryland. So Seth has done many things in many systems, including cuprates, marine materials, and others. I think one unique aspect of the work of Seth is that he is able to apply formal theories to study very experimentally relevant systems. And I think this is also the topic today. Seth, please.
Wow. Thanks for the great introduction, Lujan. And it's a real pleasure to be speaking to you all here today. Um, Lujan asked me to talk about my recent work with Meng Chung at Yale and Senthil at MIT. Senthil was my PhD advisor. So this work was focused on quantum charged liquids and minimal topological order. Um, so without further ado, I'll jump right in. Um, hold on, I think I need to. Okay, cool. My clicker should be working. So let me give you just a brief outline uh, of what I'll be telling you over the next hour, but please feel free to interrupt me at any point and ask questions. Um, so I'll start, as Lujan alluded, with some experimental motivation, and hopefully I'll motivate you why we should care about this kind of quantum charged liquid topic and if it might be reasonable to see in a real system. Um, and then I'll get into introducing quantum charged liquids by analogy with a system many of you are probably already familiar with. Um, and once I've done that, I'll get into the real meat of the new things that Meng, Senthil, and I did, uh, formalizing this concept of minimal topological order and providing some useful lower bounds on the number of anyons in some specific systems, quantum charged liquids. So uh, to give you kind of a flavor of this, I'll prove a lower bound on the anyon count in a fermionic quantum charged liquid, or at least sketch a proof. So you kind of know how to apply this. Um, and then finally, I'll discuss where we might realize this. Um, so let me just jump right in then into the experimental setting. Uh, I myself, and probably many of you, like to think about strongly correlated electron systems where electrons talk strongly to one another. Um, to make the electrons interact, we need to, or it's often helpful to confine them to two dimensions where it's hard for them to run away. So it's easier for repulsive effects to dominate over the kinetic energy. Um, and this is greatly helped by the amazing advances in atomically thin van der Waals materials, where we can, or I shouldn't say we, but heroic experimentalists can build whatever system we want to study these strongly correlated electrons. Uh, and let me just specialize a little bit and talk about a very specific system, the transition metal dichalcogenides, or TMDs, I'll refer to them. So specifically, I want to consider TMDs which form a Moiré lattice in some way. Whether that's a homobilayer, which is twisted, so you get a Moiré lattice from the twist, or a heterobilayer where there's some lattice mismatch. Um, but whatever the case, these Moiré TMD setups often have very strong repulsion on the order of like 100 millielectron volts. Um, and this is almost, can be up to 2 orders of magnitude larger than their bandwidth. So they're really quite strongly interacting, and kinetic energy is often playing a small role. In addition, they're spin valley locked, uh, which means that we can think of them having strongly spin half electrons in a single band. Um, and these spin half electrons in a single band will be described by an extended single band Hubbard model. So by extended here, what I mean is just that the Coulomb repulsion is not just on site. It's so strong that it's extending over several sites. Um, and it's exactly this extended repulsion, which is going to give rise to many of the cool quantum charge liquids we'll think about. Um, okay, so I want to show you a schematic phase diagram from this great review by Kinfei Mak and Ji Shan. Because these Moiré setups can be dual gated, you can tune two things at once. Firstly, you can tune the filling factor of the Moiré lattice just electrically, but you can also tune a displacement field between layers. And tuning that displacement field will change the position of the bands inside the Moiré-Brillouin zone, which will renormalize the bandwidth. And that will tune this ratio of kinetic energy to repulsion. So these are the two axes that we'll be considering. And I put a big quote here because I want to show you some experimental data before I bias you with this kind of cartoon picture. Okay, so I talked about quantum charged liquids that might give you a key that charge ordering or charge will play some very important role. Um, so let's think about that aspect of this system. So what I'm showing here is a plot of the essentially the compressibility of phases in these Moiré lattices, where the x-axis is tuning density. And these blue regions, which can be sensed by some exciton sensing technique, are these incompressible phases which arise at commensurate fractions of the Moiré lattice. So if I forced you to guess what's going on at these fractions where we have incompressible phases, you might hazard a guess that we're somehow breaking translation and we're getting some kind of crystalline behavior. And I would have said it's very hard to verify that guess, but there was an amazing experiment by Mike Cromie and Feng Wang's groups at Berkeley, where they top gated their sample with graphene, which allowed them to actually use an STM tip to image the underlying charge distribution in the Moiré TMD without damaging it. And what they found at filling one, so that means one electron for every one Moiré unit cell, they found this kind of very clear underlying triangular lattice. This is the Mott insulating phase. So the electrons are so strongly repulsive that there's not any electron, there's no double occupancy at any site. But then they tuned to 1/3 filling by using this dual gating. And when they did the STM, they found some translation breaking. This looks like a √3 by √3 charge order. So if we now fill in the schematic phase diagram, at a specific filling factor, say 1, you can see the Mott insulator arise. Now, of course, as you increase the bandwidth and you make the kinetic energy stronger, you're going to bias the system towards a metallic phase, a Fermi liquid phase. But nonetheless, at these fractional fillings, you see crystals, which are referred to as Wigner-Mott insulators in the experimental literature. And this, at least theoretically, you can have a really rich phase diagram by just fixing your filling and thinking about bandwidth tuning between one of these crystals and a Fermi liquid. So let me just specialize into that. That will be the main character kind of our focus today. So I'll review the experimental facts again. At large bandwidths, we have a metal with its Fermi surface in the Brillouin zone. And at small bandwidth, confirmed by STM, we have this Wigner-Mott insulator. We know from exciton sensing that it has some charge gap, and we know from STM that it breaks translation. So there's some finite value of this order parameter. Um,
Seth,
these are, yeah, Lujan. Yeah, what's up?
what is external sensing?
Yeah, oh, great question. So the exciton sensing, um, they have some exciton binding energies. So if you induce some holes and particles between these two layers, there will be some binding energy associated with that. And that binding energy is influenced by the strength of the Coulomb attraction between a hole and a particle. So if you have something like a Fermi liquid, it will screen that attraction, and you'll be able to tell that from looking at the binding energy. On the other hand, like if you have a crystal, you won't screen it because you don't have um, a compressible phase. So your Thomas Fermi screening is not there. So you're able to access actually compressible or incompressible just by looking at the exciton binding energy.
I see, but is it
Um,
some sharp measurement or is it something qualitative?
hmm. Yeah, so um, this exciton sensing technique is what allows you to plot out this kind of phase diagram here. And I would say this is just qualitative, but when you actually look at the data, it seems like there's a pretty sharp distinction
I see.
um, between being compressible, which is measured by this reflectance measurement that they're looking at,
I see.
and being incompressible.
Uh-huh. Thank you.
So in practice, it seems like it's a pretty good
Hmm. Yeah,
thing to look at.
thank you.
Yeah, absolutely. Great question. Um, yeah, so this is kind of the experimental facts as they stand. And these two phases are really different. The metal has all of these low energy degrees of freedom associated with the Fermi surface. Um, and it preserves translation, while the Mott insulator, the Wigner-Mott insulator, breaks translation is and has a gap to all excitations. So there's a big question mark. Um, and myself and collaborators, we've mainly focused on the breaking of translation, and we've kind of ignored the spin degree of freedom. I claim that this is not a big deal because the spin exchange scale in these things is actually very small, around 1 Kelvin, measured with Curie-Weiss plot looking at magnetization. That kind of makes sense because if you think about the virtual exchange process that would be necessary to create a Heisenberg coupling, it's very, very small because these electrons are quite separated. The Moiré scale is like some nanometer scale. And then once you have a further breaking of translation, it's going to be even larger. Um, okay, so we ignore spin and we just think about spinless electrons. And we thought about several interesting possibilities. I throw these up here in no particular order just to give you a sense of what we did, but I'll be choosing to focus on one today. Um, okay, so let me just give you a brief taste. So the first one is kind of the simplest scenario. We just have a first order transition where we immediately develop charge order and open up a gap between these two phases. You could also have a more exotic scenario, which is number 4. Again, a secular order, sorry. Um, where there's a second order phase transition between these two phases. So, myself, Senthil, and Debanjan at Cornell worked out some of the consequences for experiments of that phase. Um, Slightly simpler, you could also have a metal with a second order Landau-Ginzburg phase transition where you develop charge order. That charge order will then reconstruct your Fermi surface. So you'll have a CDW metal. And then as you shrink bandwidth and increase repulsion, the size of the Fermi surface will shrink to 0. You'll open up a gap and you'll become an insulator. So this is a very well understood story. But you can ask, what happens if you reverse the directions of this? That's scenario three. What happens if you develop a gap before you develop charge order? Um, so that's possibility number three. Translation is broken after a charge gap opens. And I put question marks here because it turns out I won't actually, or at least for the purposes of this talk, I won't be caring about transitions. But it will turn out that this intermediate phase between the metal and the insulator will be really interesting. And furthermore, it's not actually ruled out by the experiments because the STM can only access the charge order, while the exciton sensing can only access compressibility. So it's actually not clear which happens first, whether you open up a gap first or you break translation first in the system. Um, okay, but I've said I want to attack this problem. How will I do that? I need some kind of a model. Um, I could start with a continuum model, but that doesn't include lattice relaxation. So there's some theoretical uncertainty around where to start. Instead, I am a theorist after all. I'll begin with some very theoretical questions about this phase. Um, and I'll start by calling this phase an intermediate quantum charged liquid, or QCL. And I'll make an analogy to quantum spin liquids, which I'll make more robust as I go on. So just like a quantum spin liquid, which you may be familiar with, at the lowest temperatures, a quantum spin liquid doesn't display any spin ordering. Here we have this fractionally filled phase, which at the lowest temperatures doesn't display any charge ordering. But it's not like a metal because it's gapped, so there's no gapless degrees of freedom. And just like an analogy to a quantum spin liquid, we can guess that the ground state is going to be a superposition of many different charge orders. Um, and it will probably be stabilized by large charge fluctuations, just like the quantum spin liquid is stabilized by large spin fluctuations. Um, okay, so I made that analogy, and now let me kind of make it a little more precise by giving you an old example looked at in a new
Seth,
light. Yeah,
sorry, can I ask a
what's
question
up?
about your previous slide? You
Yeah,
mentioned something about the lattice relaxation. Which lattice are you talking about?
yeah.
The
So um, there's always this problem, which I've learned more about at CMTC, where the details of experiments are very important. Where when you have these Moiré systems, they don't like to be twisted, so you'll often have a relaxation of the Moiré lattice.
I see.
That can manifest as the lattice just looking different. Um, so sometimes rather than having like a triangular lattice, it might relax to being locally commensurate, and then there's like a phase slip um, where you might have some boundary mode. Or you can just have the presence of strain because your sample is strained, and that acts like a gauge field if you expect to have any Dirac cone. So there's a lot of lattice relaxation is a really tricky thing to handle in these systems.
I see. Okay, thank you.
Yeah, yeah. Good question. Um, yeah, so let me give you an kind of an old, and we'll reinterpret it in this new light where we're thinking about quantum charged liquids, things which are gapped and at fractional filling, but nonetheless don't break translation. Um, so let's just think about hardcore bosons, which live on the links of the triangular lattice. So here I'm showing a triangular lattice, and I'll put my bosons on these sites that I've highlighted here. Well, if I connect these sites up, turns out this is just the Kagame lattice. Okay, so the bosons live on a Kagame lattice, the sites of a Kagame lattice. Um, and I'm going to energetically um, maybe I require it by fiat, maybe I add a large energy penalty. I'm going to require that each hexagon of this Kagame lattice shares only one boson. So you can see that this hexagon has this boson here, and this hexagon has the same boson. So every hexagon has exactly one boson. And I've very suggestively drawn this kind of link that highlights the link of the triangular lattice. And that's because it turns out that requiring one boson per Kagame hexagon is exactly the same as requiring that each site of the triangular lattice is touched by one and only one of these kind of dimers emanating from the hardcore boson. Hopefully this picture makes clear. This is exactly the same Hilbert space as the bosonic dimer model. However, I'll just give an aside. In the bosonic dimer model, you often think of these spin degrees of freedom, which live on the sites of the triangular lattice, and they pair into singlets, which are living on the links of the triangular lattice or the Kagame lattice. Because all we're caring about here is charge degrees of freedom, we've forgotten that original spin. So it's just a convenient picture for us to think about dimers. Okay, so it's the same Hilbert space as the bosonic dimer model, and thus it's not at all surprising. If we add a hopping here, we'll get some ring exchange term, just like in the dimer model. So let's say we try to hop a single boson. If we hop that boson, now unfortunately this hexagon has two bosons living on it, and these dimers touch. So we're not allowed to do that. Instead, we need to do a sequence of 2 hops, which gives us this ring exchange term. Excuse me. So along with the Roxar-Kibelson potential, this has been demonstrated numerically by Mosner and Sandi to realize an extended QCL phase. So that's an extended phase where our ground state is actually a superposition of all different dimer coverings. So the ground state is a superposition of all the different ways that you can put the bosons on the Kagame lattice with this 1 per hexagon rule. And you can see there are at least 2 here, right, connected by ring exchanges. Turns out there's a huge number of them. But when your ground state is this superposition, you won't break translation because any acting with translation will just take your state to itself because every single state that satisfies this requirement is in the superposition. Okay, so this is an example of a quantum charged liquid. I said that experimentally we might have this in between our metal and in between our metal and Wigner-Mott insulator. But it was kind of, I wanted to give you an example to hang your hat on. The really important feature that we'll come back to and re-examine a lot is that this RK point, at the RK point, this is described by Z2 topological order. So this quantum charge liquid exhibits topological order. So I just want to stop here and give some obligatory quantum computing connection, which is actually, there's this experimentally relevant difference between a quantum charge liquid and a quantum spin liquid. So everything I've told you up to this point, I made analogies between a quantum spin liquid where I thought about taking spins and mapping them to hardcore bosons and turning them into this quantum charge liquid picture. But there's this qualitative difference between the two. So first of all, it turns out that gap states at a fractional filling of the lattice. So before that quantum dimer model example was at filling 1/2 per unit cell of the Kagame lattice. And if I'm at a fractional filling of the lattice and I don't break translation, the Lieb, Schultz, Mattis, Oshikawa, Hastings, I'll just say LSMOH in the future, theorem will tell me that I must exhibit topological order. So that Z2 topological order in the quantum Dynamo model is not an accident. It's required that there be some topological order there. But the QCL is kind of special because the TMDs have this very high charge exchange scale. As I said before, the charge repulsion is on the order of 100 millielectron volts. So this potentially means that we might be able to stabilize the topological order of a quantum charge liquid at a higher temperature than that of a spin liquid. So does this mean maybe more robust topological order for quantum computing? That's above my pay grade at the moment, but I think it's an interesting direction. There's this qualitative difference. Is there any other
Sorry,
differences?
Seth, did you say this is
Yeah,
qualitative difference or quantitative difference?
sorry, quantitative. I made a mistake.
Okay.
Yeah, this is really a quantitative difference of energy scales.
Mhm.
Yeah. Um, so are there any other qualitative differences, is what I wanted to say. We have this quantitative difference of energy scales, but what about some qualitative difference between a quantum spin liquid and a quantum charged liquid? And here's where fermions come back into play. After all, our experimental system has fermions in it. So let's just think about a system with fermions at filling 1/2, and we'll take them to be spinless as we have, because the spin exchange scale is so small. And let's say that we don't break translation or charge conservation. It turns out, and I'll prove this to you in a few slides, that we can no longer get the Z2 topological order we get in the bosonic analog of this because of the fermion parity. And this is related to the fact that while bosonic QCLs can be connected to quantum spin liquids through this spin to hardcore boson mapping, fermionic QCLs cannot because of this fermion parity problem. So let me just be a little more specific. So why no Z2 topological order for fermions? And let me start with bosons and I'll review the LSMOH theorem. So I have bosons at half filling, and I don't want to break translation or U1. Now, one obvious way I could not break translation, almost like a kindergartner way of thinking, is to take the boson, my fundamental particle, and split it in half, and just put half of the boson on every single lattice site. It turns out that this is exactly what LSMOH actually requires of you. You need to have a background anion with U1 charge 1/2 on each site, and we'll call that anion A going forward. If you want to prove this, one way to think about it is if you thread 2π flux, you create a Ison, and you can braid that 2π flux around a single unit cell. Because every unit cell contains half charge, that Ison will detect that half charge, and there will be a pi braiding phase. So you know that there must be some non-trivial anion. Okay, so we have this background anion A, and in a bosonic theory, there's absolutely no problem with saying that A behaves like the E particle of Z2 topological order, or alternatively, by its other name, the toroid code. So we can just require that A squared. If I knit together the two halves of the boson, I just back to the boson, which I identify with the vacuum. But for fermions, I have an issue. If U1 is unbroken for fermions, the vacuum in a fermionic TO has even charge, or said another way, the only anion that can be identified with the vacuum is one with even charge. You can kind of think of this as like the only thing we can condense in a for topological order is the Cooper pair. So we need two fermions. But let's suppose by contradiction we could realize Z2 topological order. All the anyons in Z2 topological order square to the vacuum. That's just the definition of the fusion group of this theory. And if the vacuum has even charge, this means every single anyon in Z2 topological order must have integer charge. And that tells us that a half-charge background anyon can't exist. That's a contradiction to LSMOH, so we know that we can't have Z2 topological order. So we've now kind of gone beyond the quantum spin liquid paradigm, and it's precisely because of this fermion parity.
Excuse me, a question here.
Yes.
So I'm wondering if this is the Samian order in the fermionic
Yeah. So that's a great question. So also in the Semion order, because I haven't told you that I need time reversal yet, the Semion order is in principle allowed for bosons. But every anyon in the Semion order also squares to the vacuum. And so that tells you every anyon in the Semion order also has integer charge if it's fermionic. So then I, again, don't have a half-charge background anyon. Does that logic make sense?
I think Samian squares to fermion.
Yeah. Okay, good. Yeah, so if you have some kind of a okay, actually that's a great question. Do you mind if I bring it back when I'm getting more into the proof?
Yeah, please go ahead.
So
yeah, thank you.
Yeah, I'll address that later in the proof actually. But yeah, great point. Thank you. Yeah, so let me just without thinking about semions, just see what the simplest thing I could kind of dream up if you ask me to think really quickly is. So I want to construct a quantum charge liquid, and I have this issue with fermions that I'm not able to have Z2 gauge theory. So maybe I can get around this by pairing the fermions into Cooper pairs. Oh, by the way, I just wanted to interject. Yeah, so if you have I wanted to clarify, if you have a semion S, the semion will have topological spin pi over 2. So then the semion squared will have topological spin 4 times the semion, which is 2 pi. So a semion squared is actually a boson. That might be helpful, Yingchen.
I see. Yeah, thank you.
Yeah, no worries at all. Yeah, okay. So yeah, let's think about constructing the quantum charge liquid. We have this issue with the fermion parity, and so let's just basically sweep it under the rug by pairing our fermions into Cooper pairs. And if the fermions are at half filling, the Cooper pairs are at quarter filling. And again, I'd like to show pictures to hopefully make things obvious. But let's say I take a Cooper pair and I want to put half of a fermion on each site. You can see that that'll be a quarter of a Cooper pair. So what I have is some bosons. If I forget where the bosons came from, I just have some bosons at a quarter filling, and I know I can always make Z4 gauge theory out of that. So I can definitely get Z4 gauge theory. But Senthil, of course, wanted to know, is this the smallest? Because Z4 gauge theory is Z4 topological order is quite large. There's 16 total anyons. all four powers of the E particle and the M particle and all of their respective multiples. He asked, are we sure that there's not a simpler topological order that we can get for fermions at half filling? Which was a great question, and it turns out something that's only recently been tackled. And if you are able to answer this question, it gives you a useful tool if you're ever doing numerics. So how do we even begin to answer this question? By the way, just to remind you how we got here, because I know that we've traveled far from our experimental realization. We have our experiment. We think maybe there's a quantum charged liquid which doesn't break translation, but has a charge gap. That needs to be topologically ordered, but it seems like it's weirdly complicated with fermions, and we want to know what the smallest thing is. So now we kind of really narrowed our focus, and I started to learn the formalism of unitary modular tensor category. So if you're not aware of this, or you don't know that much about it, then you're in the position I was in like 2 years ago. So don't feel too bad. For our purposes, let's just say a UMTC C, it's some bag of anyons, which are fractions of fundamental particles. And typically, those anyons are knit together with gauge fields. So if we have our boson, let's say our background anyon is half of our boson, usually there's some gauge field which confines the two. But sometimes you can find them in their deconfined phase, and this gauge field, loosely speaking, allows for the anyons to braid. So we have this kind of braiding where we take anyons around each other and they sense their histories, to use probably some Quanta magazine articles description. Okay, we have braiding, and we can also add in fusion. So if we have our background anyon, which is half of the boson, fusing two of those should give us the boson. But we also have these, and this is the case for abelian anyons. Fusing abelian anyons will only ever give you one fusion product. For non-abelian anyons, which I'm representing as these kind of larger balls, larger marbles, say, fusing can give you multiple different outcomes, so different fusion products. And there's some rules that any UMTC must obey for braiding and fusion to obey some reasonable axioms. So these are the rules of the game. They're the pentagon and hexagon equations. I'm just reproducing some from the G-cross tensor category paper that Mason and collaborators wrote. There are other works that do this, but the intro to this paper was helpful for my understanding. Okay, so these rules constrain the possible UMTCs. But we want to get even more restrictive because we were often thinking about symmetries, right? We wanted to start thinking about not breaking translation, not breaking charge conservation. So what if we add back in symmetries? This is known as, or called enriching. And if we require that each particle carries a label, so let's say our background anyon was charge 1/2. If we fuse two of them, we should get this charge 1 boson. And so the charges assigned by the symmetry must behave reasonably. So there's some additional restrictions on topological orders. And the resulting TO is a symmetry-enriched TO, or SET, for short. And I want to think about the set of SETs. So let's again say that our symmetry group is H. So let's say that H is translation and U1, because we've been thinking about those symmetries a lot. And let's say also that we're at half filling. So I'll put up our bosons with the background anyons on every site. And I want to define the set of all SETs, which are consistent with this symmetry group as well as the filling constraint. And I'll call that SET sub H. So I have some set of SETs called SET sub H. And each of these SETs is this, as I said, bag of anyons, the bag of marbles. So if we take a look at SET1 here, it has 5 small anyons, which are abelian. Their size represents their quantum dimension. And SET2 has 3 anyons with this very large non-abelian enyon. The size of SET sub h, it is infinite. Because what we can always do is we can always take some SET here and take another SET which is uncharged under the symmetry and just product them together. So we can always grow our SETs and add some bigger SETs to this kind of set of all possible. So what I just told you is that the size of the TOs in SET sub h can always be enlarged, but can they always be shrunk? And what's the smallest? The LSMOH, Lieb-Schultz-Mattis theorem, will tell us that in some situations, given filling and symmetry constraints, we can't shrink them all the way to an empty bag. We must have something. So for me to tell you what the smallest is, I actually have to be a bit pedantic and ask, what do you even mean by smallest? So does small mean enyon count? If that's what you mean by small, we can define a class, the minimal orders that respect this symmetry group H according to enyon count n. So if we think about this class of the smallest possible orders according to this classification, we'll have to exclude SET1 because this has 5 anyons, which is larger than the number of anyons in SET2. So you can kind of see that minimal according to enyon count will tend to prefer non-abelian theories with smaller number of anyons, but maybe higher quantum dimension. On the other hand, you could think about small by quantum dimension. So that minimal obeying H, which respect according to this ordinal ranking of quantum dimension. So then you'll tend to prefer SETs which have a lot of abelian anyons because they have a very small weight. So that in some sense, this is the minimal according to the weight of the bag, and this is minimal according to the number of marbles. So a great recent paper by Qiaoming, Chunka, and Meng, they thought about the minimal class according to quantum dimension. But I want to make a case for the other minimal class. Both are totally fine, but I think this other minimal class can provide valuable insights. So it was shown by Mason and probably by others. I apologize if I'm citing incorrectly, but that the enyon count of a topological order is the ground state degeneracy on a torus. So if you've ever done exact diagonalization to study like the fractional quantum Hall effect, or very much in vogue now, the fractional quantum anomalous Hall effect, or FCI, and you've tried to diagnose topological order by counting ground state degeneracy, you're familiar with this way of accessing information about the topological order. And what that means is if we're able to prove minimality, if we're able to establish some lower bound on the number of anyons, then that can be really helpful for someone doing exact diagonalization who wants to determine whether or not or what topological orders they're realizing when they find so many ground states. So this is actually already being used. Huang and Wu, they had a very recent paper where they were looking at topological orders that are realized at 3/4 filling in the fractional quantum Hall effect. They found some ground state degeneracy of 12. And we were actually able to be helpful to them even with our unpublished work, because we were able to show that this is the lower bound possible. So at this given filling with the symmetries of the quantum Hall effect, this is the lower bound of the number of ground states. And moreover, the topological orders consistent with this are all some more read-like states. So hopefully this makes the case to you that minimal order is useful, and especially if you're doing numerics, can be a really useful tool to trying to figure out what you're seeing.
What symmetries did you include in quantum Hall?
Excellent question. Yeah. So I realized I kind of threw this in here. It's not the quantum charge liquid system. For quantum Hall, all we've included is U1. So we don't assume translation, we don't assume time reversal, anything like that. All we have is U1 and fractional Hall conductivity.
I guess you're not even magnetic translation.
Yeah, not even magnetic translation. If you wanted to think about, yeah, you could include that, and that probably wouldn't change our analysis. But basically what we said is, by Laughlin's argument, if you have a fractional Hall conductivity, you know that you have a boson in the system. And you know the charge of the boson, which is just given by the Hall conductivity. And so then you can kind of construct all possible powers. And if you establish some lower bounds, and I'll walk you through how to do this in the quantum charge liquid case, you can see that all the possible states, which have a ground state degeneracy of 12 at this filling, are more read-like. I don't know if that answers your question.
Yeah, it's helpful. Thanks.
Okay, cool. Yeah, hopefully this paper will be out relatively soon, and then you can take a look. But yeah, we were able to do this kind of argument for all possible fillings, actually. So, okay. But I want to give you a flavor of how you prove these lower bounds. I told you they're useful, but let's give the listeners some practice with thinking about them. Okay, so we're going to again go back to our fermions at half filling per unit cell, and we'll think about our symmetries being translation, U1, and I'm going to throw in time reversal, just because we know from experiment that there's no signs of time reversal breaking in these TMD setups. Okay, so those are our symmetries and filling. And I have our Cooper pair construction just to kind of remind you what system we're thinking about. Okay, so we know that we have our background anion with U1 charge 1/2 on every site, which we call A. That comes from that LSMOH argument. And furthermore, A must be an abelian anion. There are many ways to see this, but I'll give you one easy kind of proof by contradiction. Suppose that it was non-abelian and had quantum dimension D, then the ground state degeneracy of the whole system would be like D to the N, where N is the number of sites. That's macroscopic, and the system is going to want to break that. So you add any interaction, anything else, it'll flow to some lower ground state degeneracy, and then we can no longer think of the same non-abelian background anion. And once you carry out this process enough times, you'll find an abelian anion. There's a more mathy argument from, I believe, Mason, Zalatel, Ashwin. There was some big paper that they were all on. But that's a simple way to see it. Okay, so our background anion is abelian. And as I've already said, we know that A squared is not the vacuum because A squared has charge 1, since A has charge 1/2. And further, A squared isn't the fermion. So you can show this by two facts. You know that the fermion, the fundamental fermion, braids trivially with everything, and it has topological spin pi. And if you use those two facts, we prove this in our appendix, you can show that no anion can square to the fermion. So A squared isn't 1 or C, and that tells us in a fermionic topological order, something must braid non-trivially with it. So we can start searching around for other anions that our system might have. I'll spoil the surprise for you. The thing that braids non-trivially with A squared is not the Vizon. However, we must have this abelian Vizon based on this argument from the Barkeshli G. Cross paper, whose braiding with every anion detects its charge. So the Vizon braids with this background anion, has pi braiding. But that means that it will braid trivially with A squared, because A squared has integer charge. Okay, so where do we go from here? Let me just walk you through kind of the proof strategy. So first, we want to find a topological order in SET sub H and upper bound our minimal order, the number of anions, with the number of anions in that topological order. Obviously, if any TO is to be minimal, it must have less than or equal to anions than any given TO we find in SET sub H. So I'm drawing a vice scripts here. So the top of our vice scripts, this upper bound is Z4 gauge theory, the Cooper pair construction. Sorry, excuse me. And that has 16 anions. And then we'll think about considering all the anions that the symmetry group requires us to have. And we'll catch our theory in a vice. So our lower bound, all the anions that our symmetry group requires, is some powers of the background anion and the Vizon. So let's find this mysterious other anion that braids non-trivially with A squared. We want to start with the lower bound, and we'll think about the powers of A and V. So there must be at least 8 anions here. This is because since A squared isn't trivial, that means that A must have order at least 4. And furthermore, V cannot be contained in any power of A. This just follows from the Hall conductivity being 0, and thus V is a boson in this time reversal invariant case. So it's a little annoying, but you can just check explicitly that the upper bound of 16 possible anions will force you to have that A to the 4th is equal to 1. And that tells you that there must exist some anion gamma, which has pi braiding with A squared, but which braids non-trivially with A squared, but has trivial braiding with A to the 4th, since that's 1. So then that must have pi braiding. Okay, if gamma is abelian, then we're done. Again, I told you I'd give you a bit of a sketch of a proof, so I won't fill in every detail. But if gamma is abelian, then you can check that there will be 16 total anions in all the powers of A and gamma. And that would saturate our lower bound. We'd kind of trap the vice. But it's tricky because gamma might be non-abelian, this thing that braids non-trivially with A squared. So let's get a little technical. I just want to give you a flavor of some of the tools that we developed. So we'll start by proving a theorem. Let A and C, so C is our topological order, be the subset of abelian anions in the TOC. So A, because abelian anions fuse uniquely, we can treat A as an abelian group under fusion. And then we'll define this subgroup, which is all the abelian anions that braid trivially with all other abelian anions. And there may be non-abelian anions that braid non-trivially with things in N, but they just have to braid trivially with all abelian anions. And the reason to consider this is because if we mod out by N, we consider the group A mod N, then braiding will be non-degenerate on A mod N. And we're able to generalize a theorem of Tachikawa and Lee that if some anyon in A mod n has order integer n, then the size of A is given by a square times the order of n, or a square times the order of n divided by 2. And moreover, that square needs to be divisible by n squared. So that gives us a kind of a very powerful lower bound. And again, this is some thorough checking, but if gamma is not abelian, you can verify that this upper bound forces you to have n be equal to 1 a squared c and a squared times c. And you can then, I direct you to Appendix D of our paper, show that all non-abelian anyons are of the form some abelian enyon times gamma for, for any abelian enyon. And furthermore, you can choose this non-abelian gamma to be such that gamma times gamma is equal to V, the Vizon, or the Vizon times A squared times C. Then you can use this formula, which is a result for fermionic TOs that also respect U1. I first encountered it in a paper by Matt Lappa and Michael Levin, which is a great paper, by the way. You should definitely read that. And you can just explicitly compute, and you'll see that if you have this non-abelian gamma, then its topological spin must be 0. But you arrive at a contradiction if you condense V, because you just get the Ising topological order, and there's no version of the Ising TO that has a non-abelian enyon with 0 topological spin. This was known, I think Kitaev in his 16-fold way classified this. So with this contradiction, we've learned that gamma is abelian, and we're done. So I realize that was a little quick, but hopefully you kind of get a feel for how you prove these lower bounds. You start out with some theory that you know you can realize, some SET in SET sub h, and that's at your upper bound. And then you think about all the possible powers of your abelian anyons, and very frequently you'll catch a specific number of anyons in the vise. So you'll need at least as many anyons as the simple theory you constructed. So it turns out that this isn't just a lower bound. So we are able to say more actually than just that we must have 16 total anyons. We can actually prove that Z4 gauge theory is the unique minimal topological order in this situation. So given this filling and this symmetry, you can check, you have to deal very carefully if translation permutes anyons. You need to be very careful to not make certain assumptions about the background enyon. But if you treat those carefully, you can see Appendix E of our paper if you're interested. We're able to show that Z4 gauge theory is actually the unique minimal theory. Okay. So I already told you minimal order is useful if you're doing ED or you're doing numerics, because this lower bound can also often give you insights into what orders you're realizing. But it turns out that along the way, we also learn things that are useful. So we have this result that I flashed on the screen about the size of the abelian subset in any topological order was useful to some colleagues of mine who were making topological orders by condensing anyons in T Pfaffian times T Pfaffian bar. So this is some huge topological order, and they wanted to see if they could get Z2 gauge theory. And our result was able to really constrain the possibilities for that. Okay, so these tools are useful in many contexts, including by saving you time. if you're trying to construct topological orders. I have some theory questions about, is minimal order more than just a tool? So there's some theoretical question. Could I take any order in SET sub H and condense some of the bosons? So say I have some very large order, and maybe this order is secretly Z4 gauge theory times some order that's uncharged under the symmetry. Can I just trivialize that uncharged order and always flow to Z4 gauge theory? Like, is there some notion of flow under condensation in SET sub H with the minimal orders being fixed points of that? Are there other useful classes of minimal orders? If so, what is their relationship to minimal by any count or by quantum dimension? And I realize that I'm quickly getting close to the end, so let me just very quickly talk about realizing a fermionic QCL. So I realize I was motivated by the experiment, but this is a really hard question, so I want to see if I can find a model system to realize a fermionic QCL. So the first thing to do that I want to do is take inspiration from the Cooper pairing construction, where I had bosons, which were Cooper pairs at quarter filling. And I just want to think, can I get a Z4 topological order that realizes a bosonic QCL at filling 1/4? So this is kind of like the dimer model example, which was at filling 1/2. But Lujan wrote a great paper on classifying symmetry-enriched topological orders. And I think he reviewed people trying to get ZN gauge theory, and it's just not very well studied at all. Z2 gauge theory is studied in all these different contexts. Dimer model, valence Fisher-Gervin, all kinds of different things realize that. But getting Z4 topological order is not really well studied. You could take some inspiration from 1/3, where people have thought about generalizations of the dimer model into a trimer model. And they've shown that they can get Z3 gauge theory, and they can actually map it to a bosonic QCL. So they didn't use that language. They used the language of Rydberg atoms, which is also cool. But we could take inspiration from that and think about a former model with rather than trimers, formers. And I'm thinking about that with some CMTC members. We've written some tensor network code that is showing some promise that we might actually be able to realize Z4 topological order. So maybe the dream is that we might be able to find a exactly solvable bosonic QCL at 1/4 filling, which gives us Z4 gauge theory. And I think that's a good starting point to try to find Z4 gauge theory in a fermionic QCL. Just finally to close out, once we understand this a simple model, maybe we can have some insight about where to find this in the actual experimental setting. So we would want to study the TMD system with realistic parameters, ED and DMRG, and think about transitions out of the QCL. So with that, I'd like to thank MIT, Senthil, Meng, also CMTC, which has been great in the 2 months that I've been here so far. And also, I'd like to thank the Laboratory for Physical Sciences, which funds CMTC, as well as the NSF and the Simons Foundation, which funded this work. So with that, I'll close. I'm a little over time, sorry, but I'll open it up for questions.
Thank you, Seth. Thank you for the nice talk. Any questions from the audience?
Can I ask a question?
Sure.
Yeah.
This is probably a naive or a general question about the symmetry-enriched topological order. So you mentioned that there are infinite many possible symmetry-enriched topological order consistent with a given symmetry H.
Yeah.
And also talked about the minimal topological order. So is there a sense that all the other symmetry-enriched topological orders are generated by these minimal topological orders? Is there a sense of structure there?
Yeah, that's a great question, and I wish I had the answer to it. So let me just flash. I was searching for, yeah, okay. So I think that's related to this theory question I had, which is whether you can kind of flow to the minimal orders. So every single order is just constructed by taking a minimal order and then producting some uncharged things, or maybe producting to the minimal order with itself again. Yeah, I'm not sure. So the examples that I've been able to come up with, it seems like everything is generated by the minimal orders, but I will be honest, I haven't checked that closely.
Generated in what
I
sense?
think like, so in the sense that if you think about, you know that every order, let's say QCL, you know that every order has to contain a background anion, and it has some charge, and it must have a Vizon. And so you could construct, you could say, let's say that my background anion has charge 1/2, but and we'll think about bosonic QCLs. So my background anion has charge 1/2, but sort of perversely, I'm going to say this is actually the E particle in the Z4 gauge theory. So E squared now has charge 1, and the M particle would not no longer be the Vizon. M squared would have to be the Vizon. But then you can think about condensing this bosonic E squared, which is charge 1, and you would get Z2 gauge theory. I don't know if that construction makes sense, but basically everything that you seem to be able to construct, there's always some anion you can condense to get to the minimal order in the examples I've thought about.
Uh-huh. Maybe Yuan, did you finish your question?
Yeah. So I was just thinking vaguely, I mean, in analogy with like representation theory, right? You have some highest width representation, and you can construct,
Yeah,
other representations, like you have a root lattice or something like that for
yeah,
the possible SETs,
yeah,
given
and
symmetric group.
that's an excellent question. You are perceptive in that many other smart people have asked me that. So I think this is on my my list of projects that I want to devote serious thought to. I think there may be some possibility here. I want to see if I can make the connection to the experiment by finding this model QCL. But for long-term theoretical study, it would be incredibly satisfying if that analogy held.
Okay, thanks.
Yeah, great question.
I have a question. Seth,
Yeah,
I guess one way to construct the topological orders here is always to first make a superconductor and then do some kind of a vortex condensation. I think
absolutely.
a large
Yeah.
class of topological orders can be constructed in this way. Then it seems the presence of a minimal topological order suggests some possible notion of minimal superconductor.
Ooh, interesting. Okay,
Like maybe
that's a good
the
question. I haven't thought
maybe
about
the
that.
structure of the vortices of the superconductor has to contain some rich structure. Otherwise, you will have even smaller topological order. I wonder if one can make this sharper.
Yeah, well, let me make a note. As I said, I have a list of project ideas. Um, is there? I have no idea. But yeah, I would expect that. So, indeed, this Cooper pair construction that we came up with was motivated by thinking about going into the superconductor and then condensing vortices. which helps you to see the C4 gauge theory. I put it in real space pictures because they're easier for cartoons, but that was how we thought of this in the first place. I mean, I guess not surprising to you. You know that Synthel has thought a lot about this sort of thing.
Yeah. Also, speaking of the emergibility, of the possible SCTs that can emerge in such a system, so in this work you have some constraint of the minimal topological order, but do you have a systematic anomaly matching framework like what we developed before to check whether a particular SCT can emerge?
No, I do not. I think that actually might be a great way to try to address this question of, is every SET just built in some simple way from the minimal one? Because if it's true that if that assumption is true, that every SET is constructed from the minimal one, then every SET that could emerge, which you can test with the anomaly argument that you've put a lot of thought into developing. So yeah, basically there should be some connection there. So if every SET that can be emerged has some, say, Z2 gauge theory hidden inside of it, then maybe you can see this with the anomaly matching argument. Yeah, so I had some brief conversation with Mason about this, but yeah, I think if you force me to say what I think the most promising way to address that question is, it would probably be some form of this, because I don't know how I would tackle it otherwise. Somehow you have to get at all the possible SETs that you could emerge, not just the minimal one, which is kind of this bootstrapping approach. And that seems like it will require more machinery, probably.
Yeah. Also, for one part, you mentioned the Z4 topological order is the unique minimal one.
Yeah.
So in this Z4 topological order, is there any in terms of symmetry fractionalization, is there any interplay between translation and time reversal? Do they always commute for all anyons?
So I believe in this case, yes, they always do. But it is not obvious. I would not be able to come up with an obvious way of showing it. So why don't I, if you don't mind, can you still see my screen?
Yeah.
I'm just pulling up the paper because I figured that some question like this may come up, and I would just scroll to the appendix. So what you can do is you can basically construct, you know that your theory is abelian. Once you've ruled out the possibility of a non-abelian gamma, you know your theory must be abelian, and you know what its generators are. And then you can very carefully show, just basically by thinking by cases. So theorem E7 is probably the important one. That this gamma must be a boson or fermion. And it turns out that when you just think about, so translation must preserve the topological spin of all anyons since it's a unitary symmetry. But it also must preserve the U1 charge. So you know that U1 in translation will commute. There might be some issue with translation and time reversal, but U1 is continuous. So there should be no issue there.
Yeah.
And if you just require that translation doesn't change the U1 charge and the topological spin, you'll see that basically every single anyon cannot be permuted by translation. So in this unique theory, the anyons are mapped to themselves under translation.
Yeah.
So it acts, yeah.
But this doesn't
Um,
answer the question whether translation and the time reversal commute.
yeah. Uh-huh. Yeah, okay. I don't know the answer to that. Yeah, that's a good point. Or it's possible that I thought about this at some point. But I think in our paper, we demonstrate that this is the unique topological order. And we mention that there are at least two SCTs. It's the same topological order, but at least two ways to symmetry enrich this.
I see.
And I don't think we did not make a very careful effort to classify all possible SCTs.
I see.
So the way that you could see that is the background enyon. Say you have Z4 gauge theory and E is your quarter charge particle. The background enyon could either be E or it could be E times M squared. So the background enyon could either be a boson or a fermion, basically. So those are two possible SATs, but we didn't really make an effort to classify all possible.
I see.
And if we had, then we probably would have thought about this.
And maybe a way to do such a classification is to develop the anomaly matching tool.
Yeah, indeed. Great. Yeah.
Actually, I think the type of analysis you did here is also something I did quite a lot in one of my papers, symmetry enriched U1 quantum spin equations. In one of the
nice.
Also, if I remember correctly, I also proved some topological orders cannot be non-abelian; they have to be abelian, and in many cases, they can be realized by some Z4 topological orders.
Oh, really?
It was 7 years ago. It was 7 years ago. I don't remember the details now.
Okay, I'll take a close look at it, and I'll make sure that this is not published yet. So I'll make sure that we cite that.
Oh, thanks. By the way,
Yeah.
one of your co-authors is also a co-author of that paper. You know who I'm talking about.
Yeah. I'm sure.
Oh yeah. Thanks for the nice talk. If does anyone else have any question?
Yeah, I still have one. Yeah, thank you very much for the nice talk first. And so just curious, is it possible to have a fermionic topological order in the fermionic quantum charge liquid?
Yeah. So I think if you have Z4 gauge theory, that would be, so strictly speaking, it's actually Z4 gauge theory times the fundamental fermion for a fermionic topological order.
I think what Yingchen was asking is, but fermionic topological order, I think what Yingchen means is some topological order, which if you do include the local fermion, then the fusion gradient is not complete, is not closed. Is this what you mean?
Yeah, this is what I mean.
Which if you don't include I see.
Yeah, in that case, you will have two vacuums, both bosonic vacuum and fermionic vacuum.
Right. Yeah, let's see. So the minimal examples that I'm aware of, they factorize as some bosonic topological order union with a bosonic topological order times the fundamental fermion. And I think the reason for that is the examples I'm aware of, the minimal orders are abelian, and any abelian topological order has that decomposition. So any abelian fermionic TO can always be written as a bosonic TO unioned with a bosonic TO times the fundamental fermion. Does that, maybe that answers the
Yeah, I
question.
see. Yeah, I see.
I think I
Yeah,
asked
thank you.
this question before, Seth. So for Lafney 130,
You-
how does this play out?
Yeah, so for Laughlin 1/3, the A enneon is the one that has topological spin pi over 3.
Yeah.
So all the enneons are 1A, A squared, A cubed is the electron, and then A to the fourth, A to the fifth, and A to the sixth is again the vacuum, 1.
Yeah.
So the bosonic topological order is 1A squared, A to the fourth. So fusion is closed. So A squared squares to A to the fourth. A to the fourth goes to the 1. Fusion is closed there, and braiding is non-degenerate, which you can check. And then you can get, so your total enneons are 1A squared A to the fourth union with that set times A cubed. So that would be A cubed, A to the fifth, and then A.
Okay.
Yeah. Yeah, but it's a very useful result if you're working with abelian fermionic topological order.
Uh-huh. But it's only true for abelian topological for abelian
Yeah.
order.
I think you can make some general arguments if you have U1 as well, even if it's non-abelian. Meng told me this at one point, and I didn't devote time to truly understanding it, so I couldn't reproduce it for you live. But apparently you can. But there's this example of SO3 level 3, which we cite in a footnote of our paper, I believe. That's some non-abelian fermionic TO, which doesn't factorize like this.
I see.
But as far as I'm aware, that's not the minimal TO for any symmetry.
So for the abelian case, what's the reference for this factorization?
I think so. We cite it in our paper. It's this Drinfeld paper. It's some math paper. Drinfeld. Yeah, okay. It's reference 62 of our paper on braided fusion categories 1.
I
It's
see.
an imposing title. 1. Yeah, but I think we may even so I made some effort to make our appendices self-contained. And I wrote this theorem. So it's theorem C27 in our appendices, and I mention where you can find the proof of that.
Okay. Thank you.
Cool. Yeah, thank you so much for the invitation. This was a lot of fun.
Yeah, and thanks for the great talk.
Yeah. Cool. See you.
Okay, bye.
Bye.